Hi. Today I'm going to discuss about one of our IP core TEDs, which is meant for automotive applications. I'm going to discuss about how to integrate and how to simulate using TED's IP core. So in a vehicle, there is a unit called engine control unit or electronic control unit. In this example, I have shown a car. So this EC is a heart of a vehicle. So this is responsible for in case of engine, so ignition timing, injection timing, or um, and vehicle dynamics, and engine heating unit, and battery control unit, as you can see on the bottom left. These are the main functions of ECU. uh, so this ECU is responsible for lot of calculations. So most of the times it involves a lot of floating point calculation. So usually it requires um, 5 to decimal places with the one plus or minus one ULP. So the accuracy is not so in high demand, but the timing is critical. So timing is what it matters in ECU. So the way to integrate our IP core is that this TED's IP core uh, can be running in Xilinx FPGA board. So this TED's IP core connected to external I/O, where it sends sends and receives a lot of signals from um, complete I would say uh, vehicle. So in this one you have engine, drivetrain, and vehicle dynamics, where which is dynamics of a vehicle. For example, a drive assist system, brakes assist system, and and the tire pressure and so forth. So the environment is external environment, or real air pressure and so forth. So this tells as the IP core. So since it's an accelerator card, so you can connect through PC via a PCI slot. So this is the usual setup, and then to get the signals, there are a lot of analog to digital and digital to analog converter from sensor and actuator signals. So these sensor and actuator signals from the unit, it will send and receive signals through these A to D and D to A converters. So usually the plant modeling, the complete system, I would say a car consists of a soft ECU. You can see on the left side, bottom left side, soft ECU, and then engine, drivetrain, vehicle dynamics, and environment. So this is a complete plant model. So usually these are mathematical models, and these mathematical models usually involve integral calculus and some probability theory techniques. So these models are, most of the days these models are and designed in Simulink. You can see I have shown uh, um, diagram on the right side. So these are Simulink models, and the box, what you can see, CPLX box is a car simulator. It's also called HILS, hardware in the loop simulation system, HILS. And ECU, you could say the FPGA board. You can say the FPGA board. So it could be connected through PCI slot, or USB slot, or any other. So this is the usual setup. So these mathematical models, this is a uh, um, ECU model. So in the ECU model, you could look at on the right side. There are injection timing model, ignition timing model, torque position thought model, and injection, as I said, injection model as well. So I don't go deeper into that. So what could be those things? But so these are, I would say, involves a lot of calculation. As an example, a snapshot I have shown here on the uh, bottom left side, you can see on the black screen. So this is a source code of um, ignition angle model. So you can see that it involves a lot of multiplication, certain constants as well, and the lookup tables and so forth. So these Simulink models, you can generate C or C++ code from a real-time embedded coder. So you can generate for any architecture of your wish. So and then it will generate the C or C++ code, and then you can compile as per your machine specific architecture. So assuming that you generated those codes, and then this on the right side, you can see this is a dashboard, a simulation dashboard, where you can see that in this dashboard you have speedometer and other digital display as well, ignition time, and then you can see on the bottom side there is an input from a soft ECU. So this is going to come from ECU, and then on the middle side you can see that there is a gear as well, 1 2 3 4 and 4 5, and a reverse gear, and there are a lot of parameters you can control it. And then so this one is this is driving from that the box what I have shown, that is simulator. So this model is this control desk is connected to that model, and then that model and the FPGA board communicate through external IO or PCI slot. So as you can see on the bottom left side. So that is the usual setup. So it is very I would say convenient to use FPGA board in this model. um, and then you can see what are those parameters, and then how the timing affects and so forth. um, yeah, so that's it. If you have any questions on uh, this integration, please do let me know through either social media channels, or you can contact us directly. Thank you.